Welcome to Empowered Learning. This video will be about implicit differentiation. What implicit differentiation is a way for us to be able to take the derivative of relationships that aren't necessarily functions by using the chain rule. So in this video, we will specifically talk about the basics of implicit differentiation. I do have other videos that talk about logarithmic differentiation and how we use implicit differentiation in that. I also have videos separately talking about taking the derivative of inverse trigonometric functions and deriving the inverse trigonometric function derivatives. And again, we use implicit differentiation to help us do that. We also have a certain type of problem in first year calculus called related rates, where we're basically solving word problems that use relationships that are defined implicitly. And so I do have separate videos on all of those things. What we are going to concentrate on in this video is just what implicit differentiation is and get some general practice with it so that we can apply it to all those other things that I've said earlier. So up until now, we have strictly dealt with functions that are explicitly expressed as one variable in terms of another, such as the ones that you see here. And so I'm saying that because if you're watching this particular video, then you've probably already learned your basics about differentiation rules. You've learned about product rule, you've learned about quotient rule, and you've learned about chain rule. But now you need to learn about how to do implicit differentiation. And so when we say that word implicit, what we're saying is that we have a function or a relationship that has a variable, let's say x in it or t in it, but we do not explicitly see it. Okay. Of course, when we explicitly see things like what you're seeing here with all of these examples is that this is a function that is explicitly defined in terms of theta. This is a function explicitly defined in terms of x. And so is this one, and so is this one. Okay. But when we have relationships or functions that are defined implicitly, then we may or may not see everything defined in terms of x. And so if we come down here, you'll see that we have examples like this one, this one, and this one, where you see that these relationships, especially this one here and this one here, these relationships are not actual functions of x, okay? Especially this one. So there's no way that we're going to be able to define y in terms of just x and have this actually be a function. For this relationship, we could if we, algebraically manipulated it enough. But again, the main thing here is that it's going to be kind of hard for us to actually take these relationships and define them as y in terms of x. Now, the reason why I hesitate to say that that all of these can or can't be written as y in terms of x is because, let's say in this case we actually could, but the whole process of taking the derivative of some type of relationship, even if it's not a function, implicitly also works on functions as well. The main motivation for the technique, though, is to deal with situations like this one, where we cannot rewrite our equation in this case as y being a function of x. So that is the main motivation for it. Okay. So that is the whole point of implicit differentiation, to be able to basically have a loophole around having to take the derivative of some type of relationship that is not necessarily a function. Now, part of the reason why this is important is because, number one, whenever we take the derivative of something, in the definition of a derivative, we have to take a derivative of a function. So if we're taking the derivative of something and it's not a function, then technically it's illegal. So this is why the whole process of implicit differentiation is so important and so slick, as I like to say. The only requirement here is that for our relationships here, or relations, we can call them in general, if we could think of each term in our relation that's not necessarily a function as a function, then that sort of lets us bypass the whole thing of needing to have a function per se to be able to take the derivative of a relation. So to try to help you see what I'm talking about here, I'm going to erase and we'll talk about each of these 3 examples here separately. Okay. All right. I'm going to switch colors here. So for this first relationship, notice that x squared can be viewed as a function in and of itself. We could view 2y squared as a function in and of itself, and we can view 64 as y equals 64, function in and of itself. For these 2 terms, of course, we could view those as 2 separate functions, and here we could view this as the product of 2 functions. So a function 2x and a function y. So a product of 2 functions would also be a function. And so that's the same deal here on the right side here. And of course, we can view both of these terms as functions. So the sort of loophole that we have to be able to actually take the derivative of relationships like this, that for the most part, especially this one, cannot be expressed as y strictly in terms of x, or x strictly in terms of y, and meet the conditions of being a function. We can use implicit differentiation to be able to work around it. Okay. So again, I know I've talked a lot about it, but I want you to understand why it is we are learning this particular technique before we sort of go down the rabbit hole and do a lot of examples and learn strategies to be able to deal with it. So what we want to talk about now is a strategy to be able to differentiate these types of relations. So first, we know that we want to differentiate both sides of the equation with respect to x, or whatever the necessary independent variable is. So the important part here is to note, and this is just my opinion here, but I have a strong opinion about it. Let's say we had something like x squared plus 3y squared is equal to 19xy. Okay. So whenever we say differentiate both sides with respect to the variable x, we're going to assume here that y is some function of x here. Okay. And that's one of the assumptions that we make whenever we do implicit differentiation, being that we have 2 variables in this particular equation. And so we're either going to assume that y is a function of x, or that x is a function of y. And so when we differentiate both sides by that, using the Leibniz notation here, what we should be doing is this to both sides. Okay. And so part of the reason why I say you should actually explicitly write this out, to use that phrasing there, is because we want to be able to see what variable we are taking the derivative with respect to. Okay. Reason being is because for this term that I'm pointing at right here, even though we see 3y squared, what you're actually seeing here is 3 times y of x squared. Okay. And so in looking at it this way, we see that 3 times some function raised to the power of 2 is actually a composition function. And anytime we take the derivative of a composition function, we use the chain rule. Okay. And so again, this is why this is important for us to understand that whenever we are doing implicit differentiation here, it's good to know what variable you're taking the derivative with respect to, because that lets you know what is the inside function, what is the outside function. Now, to make my point, what if now we decided to look at things differently here. So let's take solve. And now let's say instead we want to be able to take the derivative of both sides with respect to y. So if we did that, now it is not 3y squared that looks like the composition function, but now it's x squared that looks like it. Because now what we would see is that x squared would actually be x of y squared, where x of y would be the inside function and blah squared would be the outside function. Okay, so, and of course in this case we're thinking that x is a function of y. So the point that I'm trying to make here is that you should write this part here of doing a Leibniz notation on both sides so that you can visually see what variable you're taking the derivative with respect to. Okay. All right. So second step here is to solve the resultant equation for y prime, or dy over dx. And this is assuming here that y is a function of x. If x is a function of y, then you're going to do it this way. Okay. So what we're going to do next is some mini examples here where we're going to do the process of implicit differentiation, and we're just going to see how to actually work that out and how to employ the chain rule. So for our first example, I'm doing this example as a classic one, and I say this because even in most calculus textbooks, whenever this particular strategy or this particular concept is introduced, the first thing that they do is they will give you a problem that shows you that some kind of relationship, normally an equation, that actually can be written as a function, let's say a function y as a function of x. They will actually show that for a relation like that, this process of implicit differentiation works, because you will get the same answer if we were to rewrite the equation as y being a function of x and then take the derivative, or if you do the strategy of implicit differentiation. And so I'm going to do the same thing here, just to show you that yes, this process works even if you do have an equation that can be defined as a function. Okay, but again, the main motivation for this particular strategy is to actually use it whenever what it is that we're dealing with, the equation, is really not a function. Okay, so let's look here. Part A, we want to be able to find out the derivative of y in terms of x via implicit differentiation. So to do that here, the first thing that we see is we have our equation, and I'm going to rewrite this as y raised to the 1/2, just because I know that when I need to take the derivative of y raised to the 1/2, it's going to be easier to do if I have it in fractional exponent form, because I could use the power rule for differentiation. Now, we're also assuming here that y is a function of x. Why are we doing that? Well, number one, they told us, hey, let's do it via implicit differentiation. And number two, we're saying that the derivative of y is going to be taken with respect to x. So to be able to do that, we have to assume that y is a function of x. Okay. So this next step is the one that I was talking about in step one previously. We want to take the derivative of both sides with respect to x by writing the actual Leibniz notation here for that. Okay. And there's another thing I want to state here, and I know I've seen a lot of people do this, and some educators as well. Some educators will, and a lot of students will actually do this here, where they just do it on one side here. Now, I know a lot of people have accepted that, but I'm here to tell you that this is actually incorrect notation. Okay, you should never do this. And so one reason is because it's incorrect notation. The second reason why you shouldn't do it is because remember, you only have this on one side here. I know I've seen several students do this, and they'll apply the derivative with respect to x to the left side, but forget to do it to the right side. And so by doing it like how I'm doing it here, not only is it correct notation, but you can't forget to take the derivative with respect to x of whatever's on the right side here as well. Okay, so this is a good way to say, hey, I got to deal with both sides here. If you do it just this way, or if you just put it over here like this and don't write it like that, then you may forget to work on the other side. All right, so once we actually apply the Leibniz notation for the derivative to both sides, then of course, all I'm doing here is saying that, yes, I need to be able to take the derivative of each term separately. And of course, the derivative of any constant is 0. Now, the next step is the one that is most important. Here, the key to knowing when we need to use the chain rule and when we don't need to use the chain rule is to look at variable matching. Okay, so for instance, for this first term here, we see that we're taking the derivative with respect to x, and the independent variable of the function that we need to take the derivative of is x. So here we take the variables match here, so we take the derivative of this function normally. Okay, and of course the derivative of cosine x is minus sine x. Now notice here that the derivative that we're, the variable that we're taking the derivative with respect to is x, but our independent variable here is y. So we see that these two variables do not match, so that is what tells us to employ the chain rule, okay? And when we employ the chain rule here, remember, we're not just looking at y raised to the 1/2. It is actually y of x raised to the 1/2. So y is our inside function, and blah raised to the 1/2 is our outside function. So if you remember about the chain rule says when we have a composition function that we're going to take the derivative of, we take the derivative of the function normally, meaning we look at this as we're going to take the derivative of y raised to the 1/2 with respect to y, and that's what we have here, times, now we look at the inside function and take the derivative of the inside function with respect to x. So that's why we have this extra multiplication here in this particular term. Now, once we're here, everything else is pretty easy, okay? We just go ahead and figure out what the derivative of y raised to the 1/2 is with respect to y, and that's going to be 1/2 times y raised to the negative 1/2. And then from this step on, we're literally just trying to solve for dy over dx. So from here, everything else is pretty much a piece of cake, where we are just algebraically manipulating our equation here to solve for dy over dx. And you see in the work that I've done here that when we get there, we see that our answer is just 2 times square root of y times sine of x. And so what we are saying here is that we found the derivative of y with respect to x implicitly, okay? Meaning that what we have here is not just in terms of x. So if we actually looked at this, we're saying that y prime is equal to 2 times square root of y of x. And the thing is, we know that y is a function of x, but we don't know explicitly what it is. And so since we don't explicitly know, we just kind of work around it. And so that's the whole beauty of being able to take derivatives implicitly. I don't have to know what the actual inside function actually is to be able to know the relationship of a particular function with respect to x if it's defined implicit, okay? All right, so we see how to take this equation here, and we see the whole process of taking the derivative of y with respect to x implicitly. And again, the key to that is that any term where the variables do not match, like how we saw here, we employ the chain rule. So next, what we're going to do is we're going to see, all right, well, how does this work if we were to actually define our function as y in terms of x and then take the derivative of it, okay? Well, we see from here, all I need to do is solve for y. So I subtract cosine x from both sides, and then I square both sides. And then from here, I see that y is just 5 minus cosine x quantity squared. So y is defined strictly in terms of x here. And so now I just take the derivative of it as I normally would. Now, I know here that 5 minus cosine x quantity squared is a composition function in and of itself. So I'll be using the chain rule here. But in using the chain rule here, I'm not using it in a way to where I'm taking the derivative of this function implicitly, okay? So this is something different. So I look at this as taking the derivative of the outside function with respect to the inside function, or as I like to say, we take the derivative of blah squared. And so the derivative of blah squared would be 2 times blah. And then we'll multiply that times derivative of blah, or the inside function, with respect to x. And so here we know that the derivative of the outside function with respect to the inside function is just going to be 2 times 5 minus cosine x. Derivative of the inside function is just going to be sine x, because derivative of a constant is 0. Derivative of cosine is minus sine, and minus and negative is the same as addition. Okay. Now, if you notice here, the answer that we got for dy over dx looks a little different than it does here. Okay. But notice that the one thing that's different about it is that here we just have square root of y, and here we have 5 minus cosine x. If you think about it, 5 minus cosine of x is the same thing as square root of y. So I could come here and just rewrite this as 2 times square root of y times sine of x here. And you see that these two methods of being able to take the derivative of this equation to find dy over dx actually ends up being the same thing, okay? And so that's really the point of these classic examples, is to make sure that you know that, hey, you can do this implicit differentiation technique regardless of whether you have an equation that is a function or whether it's not a function, okay? It's just more useful whenever the equation does not represent a function. All right, so now we're going to do some other examples here where we're going to get some practice employing this technique of the implicit differentiation. So here's our first example. So we're asked to find dy over dx. So here, the first thing I'm going to do is I'm going to take the derivative of both sides of my equation here with respect to x by writing the Laplace notation for it. And again, I am strategically doing the d over dx notation here to remember that I have to work on both sides of my equation. So now from here, notice that we'll make an arrow down here. So this first term, the variables match. So I'm going to take the derivative normally. So the derivative of x cubed is 3x squared. The second term, the derivatives don't match. So here for the second term, I have to take the derivative of what I see here with respect to its inside variable, which is y, times the derivative of the inside function or variable here with respect to x. And then, of course, the derivative of any constant is 0. So from here, we have 3x squared. The derivative of y cubed with respect to y is just 3y squared times dy over dx. And now at this point, we're pretty much on easy street because we just need to figure out what dy over dx is. So we subtract 3x squared from both sides. We'll get 3y squared times dy over dx equals negative 3x squared dy over dx. If we divide both sides by 3y squared, will end up giving us this, which ends up with just a negative x squared over y squared. Okay. And so our answer here would be dy over dx is going to be minus x squared over y squared. And again, we are assuming here that y is some function of x, but we don't know explicitly what it is. And for what we're doing now, we really don't care what it is. Now, in all actuality, we can rewrite this particular equation here as y being a function of x, but we're acting, whenever we talk about taking the derivative of this equation implicitly, we're acting as if we don't know what that particular function is. Okay, so if we wanted to just know what it was explicitly here, I could just subtract x cubed to both sides and then take the cube root. So this would end up being, let's get the equal sign looking right here. So this would end up looking like cube root of 1 minus x cubed here. And so that's actually what y is. So if we wanted to, we could put the cube root of 1 minus x cubed down here and then square that. But again, implicitly, we can just leave the answer like this. All right, so let's look at the next example. So for this example, there is no way that we are going to be able to rewrite this equation as y being a function of x. So here, we really do need to be able to take the derivative of this particular equation here implicitly. So again, we're going to do the same thing. We're going to take the derivative of both sides with respect to x. I'm just going to take the time to write it here. Okay, and so now from here, when we actually execute, notice that we need to do the product rule here because we have the product of two functions here that I need to take the derivative of. So if we use the product rule here, product rule says I take the derivative of the first function, which is just dy over dx, times second function, so derivative of first times the second, plus first times derivative of the second. Now, on the other side, we do the same thing. We take the derivative of x with respect to x times sine of y squared. And then we add to that first times derivative of the second. Okay. So, of course, here our dy over dx, that is what we are looking for. So we definitely want to keep this term as is. For the next term here, notice that we have y times, and since these variables match, we will take the derivative of what you see here normally. Okay. Now, sine of x squared in and of itself is a composition function, but we're still going to use, the chain rule, but we're not going to use the chain rule in an implicit manner. Okay. So we're just going to take the derivative of this normally. So the derivative of sine of x squared, we know that the derivative of sine of blah is cosine of blah, where blah is x squared, times the derivative of the inside function here. And of course, the derivative of x squared is just 2x. And I'll come back and clean that up in the next step. For the right side, we know that the derivative of x with respect to x, all that is just 1. So we just have sine of y squared in our first term. For our second term, we have x times, and then here, notice that the variables do not match. Since the variables do not match, then we have to take the derivative of this by using the chain rule, but we're going to do it implicitly, okay? And so if we do that, we see that the derivative of sine of blah is just cosine of blah. And now we take the derivative of the inside function, which is y squared with respect to x. Okay. And so here, do you see that our variables don't match here? So here's where the implicit part comes in, because we are assuming that y is going to be some function of x. So this y is going to act like an inside function. Okay. So if I was to implicitly take the derivative of y squared with respect to x, all of this would end up being 2 times y, which is the derivative of y squared with respect to y, times derivative of the inside function, and that is just y itself. So that's dy over dx. So now that we have all that together, then what we want to do is clean up some things and basically solve for dy over dx. So here we know that x squared, the derivative of that is just going to be 2x. So we have that. We also know that this term has a dy over dx in it, and this term has a dy over dx in it. So we want both of those terms to be on the same side and have the other terms be on the other side of the equation so that we can get dy over dx by itself. So here I'll have dy over dx times sine of x squared. And all of this would need to come over on the left side here. So I'm going to subtract both sides by what we see here. So that's going to be a minus 2xy, because we got subtracting, so that's minus. We got the 2, we got the x, we got the y. And then that's going to be times cosine, got hung up there, cosine of y squared. Okay. And I believe that's all for that one, equal. Now on this side, we have sine of y squared. But notice that on the left side here, we haven't dealt with this yet. So we're going to have to subtract both sides by this term here. So this is going to be a minus 2xy, because we got the 2, the x, and the y. And then cosine of x squared. Okay. And, oh yeah, forgot about that. Sorry, y'all. Yeah, there's supposed to be a dy over dx written here, but I didn't write it. So let me make some room for that. All right, so this dy over dx is equal to sine of y squared. All right, so I think I was able to fit it all in there. All right, so now that we have this, of course, we can factor out the dy over dx to both terms here. So now what I can do, and this is what in my mind I was doing this earlier, but now is actually a proper time to do it. I can actually go ahead and separate this to where we just factor that out. And because of that, this actually goes away here. Okay. And so now we see that all I need to do now is just solve for dy over dx. And all that entails is me dividing both sides by all of this business here. And so if I do that, that would be dy over dx is equal to sine of y squared minus 2xy cosine of x squared. And we take all of that and we're going to divide it by sine of x squared minus 2xy cosine of y squared. And so that would be our final answer for the derivative of y with respect to x defined implicitly. So in this next example, we're really going to see an example of how we can actually find the derivative of some function when we really don't know what that actual function is. Okay. So we're given that g of x plus x times sine of g of x is equal to x squared. And all that we're told to do is to find g prime of 0, meaning find the derivative of g with respect to x where x is 0. Okay. And so the hint that I have here is that we want to try to figure out what g of 0 is first, and then do implicit differentiation on the equation with respect to x to actually find out g prime of 0. So let's take that hint into consideration here. So if I take this equation here, if we find g of 0, that just basically means I want to plug in 0 everywhere where I see x and solve for g of 0 if I can. So if I do that here, so when x is equal to 0, we'll get g of 0 so g of 0 plus 0 times sine of g of 0 equals 0 squared. Of course, if we're looking at all that, it's real easy to see here that since 0 times anything is 0, all that goes to 0, and 0 squared is 0. So it just turns out that g of 0 is just 0. Okay. Now, what we want to know is g prime of 0. But we're going to use this fact to help us out in trying to find out what g prime of 0 is. So now what we're going to do is take the derivative of both sides of this equation here with respect to x. In other words, we are about to take the derivative of this equation implicitly. Okay, so in doing that, this first term here, we just take the derivative of the first term with respect to x. So that's just going to be dg over dx. For the second term, notice that we have the product of two functions here. So we need to do the product rule. So the product rule says take the derivative of the first times the second plus the first times the derivative of the second. And on the right side, we see that the variables match here with the derivative and the independent variable of the actual function. So we just take the derivative normally, and that will be 2x. And I need to go ahead and close my brackets here. All right, so now we know that dx over dx here, this is just going to be 1, okay? And there's nothing else I could really kind of work with now, so we just need to do some more algebraic manipulation here and actually execute these derivatives. So we got dg over dx plus sine of g of x plus Yeah, that's a big plus sign. Make that a little smaller. So plus, and now we have x times, and notice here that the variables do match, but we have a composition function here. So we will be employing the chain rule, but in doing this, we won't be taking the derivative of this implicitly, okay? So this is just regular old chain rule here. So the derivative of sine of g of x, using the chain rule, will be cosine of g of x times the derivative of g with respect to x. And I could write it this way, or I can write it as dg over dx, okay? And so since I already have this as dg over dx here, I'm going to write it like that for now. If you feel comfortable just writing everything as g prime of x, be my guest. All right, so now, of course, the right-hand side is just 2x again. And so now we just need to solve for dg over dx. So here, I'm going to go ahead and write everything in terms of prime now. So we're just going to say this is g prime of x here, g prime of x here. All right, so at this point, these two terms with the g prime in it, I'm going to go ahead and factor that out. So I have g prime here, and I also have this term that has a g prime in it. So I'm going to have that, so it's going to be x, oh, sorry, forgot the first term. So this will be 1 plus x times cosine of g of x. And then, of course, we have the plus sine of g of x here, and this will equal 2x. Now, if I subtract sine of g of x from both sides here, and of course, what I'm going to end up getting is g of x, g prime of x times is 1 plus cosine, 1 plus x times cosine of g of x, and that'll equal to 2x minus sine of g of x. So I'll go ahead and write that step. Now, at this point, remember, our goal is to find out what g prime of 0 is. So what we can do now is we can say, let's let x equal 0 here, okay? So let x equal 0, then, I don't know why it's always doing that, but we'll just work with it. Then, so now we're going to plug in 0 everywhere where we see x. So this will be g prime of 0 times 1 plus 0 times cosine of g of 0 equals 2 times 0 minus sine of g of 0. So again, here we see that g of 0 is just 0. 2 times 0 is 0. G of 0 is 0. And so because of that, we see that cosine of 0, all of that is just 1. But 1 times 0 is 0. So all of this just ends up being a big fat 0 for that term. Here we know sine of 0 is 0, so all of this just ends up being 0. So all we have left is 1 plus 0, which is 1 inside the brackets here, times g prime of 0. And so on the left side, all of that just simplifies to g prime of 0. On the right side, we just have 0 minus 0. So we just have g prime of 0 is equal to 0. And I now apologize because we did all this work for something so unsexy as g prime of 0 is 0. But that is what the derivative of that function g of 0 is evaluated at 0. Now, we've found the answer here, but let's take a look and talk about what does this actually mean, okay? So to be specific here, we have that g prime of 0 is 0. And if we look back at the beginning of our problem here, we wanted to know, we found out what g of 0 was, okay? So here we're given that g of 0 is 0 and that g prime of 0 is 0. Now, both of these things work together to let us know something about our function g of x at some point on the graph here. So remember that g of 0 equals 0. All that really means here is that I have the point 0, 0 on the graph of my function, okay? So I know that. Remember here that g prime of 0, if you remember that anytime we have the derivative of something being 0, that means graphically speaking, we have a horizontal tangent line, okay? Meaning that our graph is either a horizontal line or it's peaking or dipping there. So what this tells us here is that we have a horizontal tangent line. So if we don't know much else about our graph here, what we do know, let me try to label this. What we do know is that we have a point on our graph that's 0, 0, and we know that the slope of the tangent line is also 0. So we know that the graph is basically flat at the origin. Okay? So this whole problem is basically saying that, yep, we know that the point 0, 0 is on the graph and that it's going to be flat at the origin. Now, what it does after that, we don't know, but at least we know that. So for our last example here, we're going to look at a problem to where we really do have to use implicit differentiation to be able to figure out what the derivative of this particular relation will be when x is 0. Okay? And so as you can see here, this particular equation here is called a cardioid. Okay, and as you can see, it kind of looks like a heart. And what we're being asked to do is to figure out what is going to be the equation of the tangent line to this particular curve at this point. So in other words, basically, what is the equation of this line here? Okay. Well, before we even get started, we know that the line is going to have a positive slope, and we know that our y-intercept by definition is going to be at y equals 1/2. So before we even begin, one of the things that we know is that this is going to be y equals mx plus 1/2. Okay, that much we already know. The one thing that we do not know is what our slope is. But we do know that the slope of this tangent line can be found from finding the derivative of our function y, which we don't explicitly know, but we're going to find the derivative of it implicitly in terms of x, okay? So to start off here, we know that we need to take the derivative of both sides of this equation with respect to x. So we basically need to do this. Okay. Now, remember that y is assumed to be a function of x here. So anytime we see y in our equation here, think of it as y of x. So in this term, it is y of x squared, which makes it a composition function. Here, this is 2y of x squared. So it makes this particular term a composition function. Okay. All right. So in doing this, if we take the derivative of the left side with respect to x, for the first term here, the variables match. So we just take the derivative normally, and that will just be 2x. Plus, here we see that the variables do not match, so we have to employ the chain rule. And so the chain rule, take the derivative of y squared with respect to x, is going to be 2y times dy over dx equals. Now we do the same thing on the right side. So notice here that we're taking the derivative of blah squared. So here we see that we're dealing with something that is a composition function to begin with. So the derivative of blah squared is going to be 2 times blah. And blah is just going to be all the stuff that's in the parenthesis here. Times, now we need to take the derivative of the inside function with respect to x. Yeah. Let's back that up. Okay. So for this next line here, we're just going to say 2x plus 2y, and I'm going to do y prime here just to cut down on the amount of writing I need to do. Equals, so here I'll go ahead and distribute the 2 here, so this will be 4x squared plus 4y squared minus 2x. And all of that will be multiplied by whatever we have here. So now that we're here, kind of do the same thing. We take the derivative of each term. The first term, the variables match, so we take the derivative normally. And so we'll end up getting 4x plus. Variables don't match here, so we'll end up doing the chain rule. So if we take the derivative of 2y squared with respect to y, that would just be 4y. But then we have to multiply that times the inside function, which is y. So that will be dy over dx. And then minus, take the derivative of x with respect to x, that is just going to be 1. Okay. And again, our dy over dx is y prime. So just to cut down on the amount of writing I have to do, didn't mean to do that. Just going to erase this and write y prime in this place. Okay. All right. So now at this point, we want to find out what y prime of 0 is. Okay. Now, notice that we have to find out what the derivative is at this particular point. So here, this is going to be our specific x value. This is going to be our specific y value. And again, what we're trying to find is this. So to keep from having to do all the algebraic manipulation to figure out what y prime of 0 is algebraically and then substitute in 0, we're going to cheat. And so we're going to cheat by just basically saying when x is equal to 0 and y is equal to 1/2, we'll just say y prime of 0 is question mark. Okay. So here, everywhere where we see an x, we're going to replace it with 0. Everywhere where we see a y, we're going to replace it with 1/2. And everywhere where we see y prime of 0, we're going to replace it with y prime, we're going to replace it with y prime of 0. So looking here, and I'm going to do this in a different color here. So at this point, we're going to say 2 times 0 plus 2 times 1/2 times y prime of 0 equals, and then here we have 4 times 0 squared plus 4 times 1/2 squared. Come on. Yeah. All right, so that's 4 1/2 squared minus 2 times 0. And then we'll multiply that times what we have here, which is 4 times 0 plus 4 times 1/2 times y prime of 0 minus 1. And so now from that, of course, we can see that there's a lot of simplifying that's going to go on. This will be 0. This will be 1. 0. 1/2 squared is 1/4. And 4 times 1/4 is just 1. 0. 0. 2. So once we're done with that, then we just have 0 plus 1 times y prime of 0. So all that's just y prime of 0. On the right hand side, we have 0 plus 1 minus 0, which is just 1, times 0 plus 2 times y prime of 0 minus 1. So all this is just 2 times y prime of 0 minus 1. And of course, all that's just going to be 2 times y prime of 0 minus 1. So here we can just get rid of all this and that, and I'll just rewrite it over. This is 2y prime of 0 minus 1. And so from here, we have common terms here, so we'll get that all on the same side. So we'll have y prime of 0 minus 2y prime of 0 equals minus 1, which means that we have minus y prime of 0 equals minus 1, which in turn means that y prime of 0 is a positive 1. And why do we want to know what y prime of 0 is? Because we know that even though we don't explicitly know what the function y is in terms of x, we know that the derivative of this function y evaluated at 0 is going to be the slope of the tangent line, and that is the thing that we need here. So now that we have that, we can actually find the equation of the line. So the equation of the tangent line is simply just going to be 1x plus 1/2, or simply just x plus 1/2 here. Okay, so that would be the equation of the tangent line of this particular relation going through the point 0, 1/2. Okay. And again, the thing that is special about doing all of this is that we had a equation here that was not a function, and we knew that because this particular relation here did not pass the vertical line test. So if you look here, it is not passing the vertical line test. But yet we were able to find out what the derivative of y was in terms of x. All right, so this concludes this video on implicit differentiation. I hope that this video gave you a good idea of what it is and a nice succinct strategy to evaluate equations for its derivative of one variable in terms of the other by doing it implicitly. Take care.